All right, we are, of course, we already worked through chapter 6 concepts. We are now in chapter 7. Just recall the cross product of two sets, A cross B. The elements, it's a set, of course, so we open set brackets. The elements are ordered pairs. So of the form, say, little a comma little b, it's parentheses, of course, these are ordered pairs, such that little a comes from the set big A, right? And little b comes from the set big B. So of course, just to remind, this is called an ordered pair. I think everybody knows that here. And we have two coordinates, right? A is the first coordinate, and B is the second coordinate. Right? We have two coordinates, A and B, first and second coordinates. So here's an example of a familiar function. But it may not be the way that you are used to writing it. But this function, I guarantee you, you know this function. I'm going to start with example 1 again now that we're in a new chapter. F is going to equal the set of ordered pairs of the form x comma x squared, such that x is in the reals. Now we are told x is real. So we know this first coordinate is a real number. The second coordinate is x squared. Well, that's going to be real, of course, if x is real. And so this is a function from the reals to the reals. This f is actually a subset of the reals crossed with the reals. Both coordinates come from the reals. You probably are familiar with this other notation. F of x equals x squared. Or you probably saw in high school, y equals x squared. You know, this is your basic parabolic function that's got the vertex at the origin, right? If we graphed it, it looks, you know, like that. Something like that. Not quite like that, but right. Okay. So, but this is the notation that is more common at this level, is for this course, because it's a discrete math course. So we like to think about the points on this curve as ordered pairs. You know, like the point 2, comma 4. And we think of the first coordinate as the x coordinate and the second coordinate as the y coordinate, right? Look, y is f of x. You know, this is f of x. X squared is y. That is the function value at x. X is the independent variable. Y depends on x. So, you know, depending upon what x is, y will take on particular values, the square of x. So let's get a formal definition now of a function for our purposes. A definition. Here we go. Given non-empty sets A and B, a subset of A cross B, we'll call it F for function, obviously, is a function from A to B That's what we're defining, a function from A to B. And it's denoted by this notation. This notation is reserved for functions F colon A arrow to B. And that's the way we read it. We read this F from A to B. So a subset of A cross B is a function from A to B if two things happen. One, each X in set A has at least one corresponding value Y in B such that the ordered pair X comma Y is an element of F. And two, each X in A has at most one corresponding value Y in B. Such that the ordered pair X comma Y is in F. So we have at least one corresponding value Y and at most one corresponding value Y. In other words, each X in A has exactly one corresponding value Y from B such that XY is in F. The existence of at least one Y for X is called like the existence clause. There does exist a Y that pairs up with X. The at most one corresponding value Y for X is the uniqueness clause. The corresponding Y is unique for X. Okay? So we say the image of X exists. And here we say the image of X is unique. So it's an existence and uniqueness claim about a partner, Y, for the X coordinate. Now notice set A, this is a function from A to B, is called the domain of F. So we're going to get a little bit more bang for our definition buck here. A is called the domain of F. And set B is called the codomain, not the range, folks. The range is something else. B is the codomain of F. So the domain, the codomain. If X comma Y is in F, we also write F of X is equal to Y. And that's probably the notation that you're used to seeing. Okay. All right, let's look at some examples more. Example 2. Let's let A be the set containing little a, little b, little c, little d, little e, and B be the set containing little s, little t with a tail, w, y, z. So just a couple of finite sets. We're going to look at a finite function here. So 1, consider this subset of A cross B. I'm going to call it F. F is a set. It has ordered pairs because it's a subset of A cross B. The first ordered pair is little a comma t. Second ordered pair, B, T. Third ordered pair, C, Y. D, Z. And E, comma T. Close that up. Is F a function from A to B? And we're going to explain or verify. So what are we checking? We're checking that each x in A, because the first coordinates are coming from set A, has at least one corresponding y value from B, and that each x in A has at most one corresponding y value from B. So let's check. Let's check these elements of A. They're appearing as the first coordinates. Let's make sure each one of those is paired up with exactly one element from B. Well, A has one image, namely little t. B has one partner, little t. C has one function value, y. I'm saying it a bunch of different ways. Z is paired up with, D is paired up with Z, and the image of E is T. So each of these second coordinates does come from B. No first coordinate is paired up with two different separate coordinates, second coordinates. So the answer is yeah. Yes. Each element from the domain A has exactly one, I'll put it in quotes, partner, what's also called an image from set B. Partner. Okay, so this is a function. Let's look at another subset. Is G given below a function from A to B? Here's G, folks. It's the set that has little a, comma, little s, little a, comma, little t, little b, comma, little t, little c, comma, y, d, z, e, t. Is that a function from A to B? What do you think? Speak up.
No,
No, why not?
there are A is matched with 3 things from set B, and T is matched with three things from set A.
So A is matched
True.
with two elements from set B, right?
Yes.
It's not a problem that T is matched with numerous elements from A. Look, that happened in F. T was the image of A, T was the image of B, and T was the image of E. That's not a problem to have a second coordinate be the same for numerous different first coordinates. That's not what this definition says. This definition says that each X has exactly one partner. It doesn't say each Y can only have one partner. But it is not a function for what you said first, Hans, and that is A is paired up with S, but A is also paired up with T. And that breaks the uniqueness clause in the definition of a function. Each X and A has at most one partner. Sophie, question?
Yeah, I mean, you kind of just said it. I was just going to ask you if you can break down the definition again, because it seems like it's the same thing written twice, except for at least and at most. So it says X is an element of A, has at least one corresponding value Y in set B, such that X, Y is an element of the function. So it's the definition is just confusing me. So I don't really follow like the second. I mean, I don't really follow the examples.
Well, the definition says if you look at each element of A, these are the domain elements. Each one of these has to pair up with a Y. There's got to be a Y that it pairs up with. That's what at least one means. It means, there's got to be some Y that each of these will pair up. A's got to pair up with some Y, B's got to pair up with something from B, C's got to pair up with something from B. It doesn't have to be this Y, okay? Just, some element from B, okay?
Okay.
But at most one means if you look at an element of A, like this one, little a, it can't have two different partners from B. It's got to have one, but it cannot have more than one. Does that make sense? Well, see, that's what I'm trying to show you here.
Okay,
This is not a function because this A has two different images, two different partners, and that's not what a function can do. So the answer is no, because the element little a in A has images S and T from B, i.e. AS is in a G and AT is in G, violating part 2 of the definition of a function. Because part 2 says the image, the Y has to be unique, that each element in the domain has to have just one partner, and A's paired up with two different elements. Let's try another example and see if we can understand it by looking at even more examples, okay? Is H a function from A to B? Here, I'll write the A up here where you can see it. A is a set containing little a, little E, and B is the set containing little s, little t, little w, y, z. And here's H. H has A comma S, B comma T, C comma W, D comma Y. And here's the definition of function, again, the two-part definition. Does H satisfy the definition of function?
Is it no?
It is no. Why do you think no?
Because it breaks the first rule.
Yeah, each element of the domain, each one of these elements has to have a image, a partner, a second coordinate that exists. You know, there has to exist a Y to pair up with A, and there has to exist some element from B that pairs up with little b, and there has to exist an element over here in the codomain that pairs up with C and with D and with E. But look, E doesn't appear as the first coordinate of any ordered pair. E did not have a partner. So the existence requirement of an image for each domain element fails for H.
Does it also fail for the second one as well, since it doesn't have any, the set doesn't have Z in it?
A, B, C, D. No, oh, no, there's no requirement that every element in the codomain is the image. It just requires that every element in the domain has an image.
Okay, thank you.
Uh-huh, good. So no, because E is in A, but E does not appear as the first coordinate in any ordered pair or of any ordered pair in H. In other words, E has no image point under H. It doesn't map anywhere. And I think the arrow diagrams that we're going to look at next are going to help with this concept. Let's look at some pictures. Arrow diagrams. For functions. You'll like these because pictures really do help. Here's our example 3. We're going to let set X equal the set containing 1, 2, 3, 4, and 5. And we're going to let set Y, big Y, be the set containing little a, little b, little c, little d, and little e. Oh, and little f. I want 6 elements. 1. Let H be a subset of X cross Y be the function, and I'm just going to go ahead and use functional notation, H from X to Y, defined as follows. Here's H. H is the set having 1 comma little b, 2 comma little c, 3 comma little e, 4 comma little e, and 5 comma little c. Draw the arrow diagram. for H. I'm going to show you how to do it, of course. And then the second thing we're going to do is we're going to find the range of H. We'll get a definition and we'll come back and we'll find the range of H. But first I want to draw the arrow diagram because then it's easier to talk about the range. All right, so to draw an arrow diagram, I'm going to draw kind of an oval shaped circle for X and an oval shaped circle for Y. These are my sets. And we're drawing H. I'm going to put the elements of X into this set X, and I'm going to separate them out so I can see, and I'm going to label on the left because I don't want my labels for my elements to get in the way of my arrows. So 1, 2, 3, 4, 5, those are the elements of the domain X. Now the codomain Y has A, B, C, D, E, and F in it, and I'm going to put its labels on the right of the points so that I'm out of my own way when I draw the arrows. Okay? All right, so how do we draw the arrows? It's exactly what you think it should be. 1 maps to B, right? This first order pair says 1 pairs up with B. 1 maps to B. So we draw an arrow from 1 to B. Folks, it's an arrow diagram. Line segments don't cut it. You have to have a tip pointing to the image. So the arrow goes from the domain, it initiates in the domain, it terminates in the codomain, so the tip is in the codomain. 2 maps to C, so I'm going to put 2 to C. 3 maps to E, okay, so 3 is going to E. 4 maps to E, okay, so 4 is also going to map to E. 5 maps to C. Okay, that's the arrow diagram. So notice this. The visual check that H is a function is this. Each element in the domain X has exactly 1 arrow coming from it and pointing into the codomain Y. Each domain element in set X has exactly 1 arrow coming from it and pointing to an element in the codomain Y. So if we went back, for example, and drew the arrow diagrams for function H, it's right up here, there would be no arrow coming out of point E. And that would be the visual check. You'd have a domain point that didn't have an arrow and didn't have an image. So an arrow diagram makes it easy to visually check. And the thing that went bad with the subset of A cross B, G that wasn't a function was that A would have 2 arrows coming from it. But what you want is exactly 1 arrow coming from it. See, that's what the at least one y and at most one y means? It means there's exactly one y that pairs up with x. That's the significance of the at least one together with at most one. Questions? Let's define the range of the function.
I had a quick question about that. So on the test, when we answer, do we have, can we say, oh, this is not a subset by the second rule, or do we have to state what the rule is?
Ah,
in the answer?
if I want you to know the number of the rule, I'll give it to you.
Okay, thank you.
Uh-huh. But you have it in your notes and you do get an open book test, right?
Right.
Given a function f from x to y, the range of f, that's what we're defining, the range of f, denoted by R in G of f, is this set. The range of f is the set of y in the codomain, big Y, such that there exists an element little x in the domain big X, where f of x is equal to y. In other words, folks, the range of f is the set of elements in the codomain that actually get hit by an arrow. That's the intuition behind this. The range of f is the elements in the codomain, here it's y, that get hit by an arrow. These are the images of some domain element, or several elements sometimes. So now if we go back and look for the range of H here, it's pretty easy to see the range of H. What is the range of H here? What are the elements that actually get hit by an arrow? Anybody?
B, C, and E.
Exactly. Now, if you don't draw an arrow diagram and you want to know the range of H, just look at the second coordinates. Those are the elements that would get hit by arrows, B, C, and E. It's okay that C gets hit twice. It's okay that E gets hit twice. Nobody says that's no good. Okay. And that brings us to the idea of the image and pre-image, but let's do one more example. Shall you just one more arrow diagram here, so that you feel comfortable with this. Let's let X be the set containing 1, 2, 3, 4, and 5. And again, Y is going to be the set containing little a, little b, little c, little d, little e, and little f. And we're going to define K from X 2y. Folks, when I use this notation, k colon x arrow to y, that means it is a function. We reserve that notation specifically for functions. So we're going to define k as follows. K is this set of ordered pairs. 1 comma little a, 2 comma little a, 3 comma little a, 4 comma e, and 5 comma d. Draw the arrow diagram. Find the range of k. So we just, we want to get comfortable with doing this. Just want to make it large enough that I can really see, and make sure that you don't use line segments. These have to be arrows. So that's called an arrow diagram. This is for K. One goes to A, 2 goes to A, 3 goes to A, 4 goes to C, and 5 goes to D. What's the range of K, everybody?
A, C, and D.
Good. Thank you. Questions? Okay, so we've been going at it for an hour. I'm going to pause and you're going to. So we are back, and thanks for the 5-minute little breather here. Images and inverse images, because I've been using the word image, but we need a definition here. Let's get a formal definition. And then inverse images is when we look backwards and see what hits something. Images of a point, or what it hits. Maybe you'll take a few of the points in the domain and say, hey, what's the image of that subset? And just look at the arrows out of that subset. And then inverse images, we go back the other way. Given a function, f from A to B, so we know A is the domain, B is the codomain, and subsets, we got to play the game with subsets. C is going to be a subset of the domain A, and D is going to be a subset of the codomain B. We define one, f of C. This we read as f of C, oops, that's an of, or we read it the image of C under F. So what is it? It's the set of Y values over in codomain B such that there exists an X in C where f of X hits that Y. F of X equals Y. And so the intuition, folks, behind this, and it is nice to have an intuition. F of C is the set of elements in B that get hit by arrows coming from elements in C. Okay. And we'll, of course, we'll look at examples, but let's go ahead and get the other definition, the inverse image of D. F to the minus 1 of D. Remember, D is a subset of the codomain. So when we see F to the minus 1, we're looking backwards. It's the set of X in A such that F of X is in D. In other words, it's the X's in A whose arrows wind up inside D. So the way we read this is the inverse image of D under F. We're looking backwards, like we kind of run backwards along the arrows. And the intuition is nice to have here. F inverse of D is the set of elements in A, the domain, whose arrows terminate or end inside set D somewhere. They hit something in D. Okay? So let's give it a shot, shall we? Let's go back to example 3. And let's play the images and inverse images game. This might be one of the times when PowerPoint might be cool to have. You know, I'm not a PowerPoint person. It's not that I don't know how to make PowerPoint. It's just that I like you to see what's going on. So, and I like you to see how long it takes to actually do stuff. I like to model writing mathematics, doing mathematics. It's like a Zen thing here. All right, so remember H was this set. 1 went to B, 2 mapped to C. 3 mapped to E. 4 mapped to E. And 5 mapped to C. So A. Oh, a picture might be good. Get a little wider. Okay, so we're going to find H of C, where let's just start with C is going to be the set containing 1 and 2. So here the function isn't F, it's H. So it's H of C instead of F of C. But according to the definition, it's the Y's over in the codomain. Of course, here the domain is X and the codomain is Y, it doesn't matter. But in the codomain, where there is an X and C that hits the Y. So let's look at, it's like you can just think about 1 and 2, like you can put them together in a little bag. That's a little subset of X called C. And we're just looking for the arrows that come out of this subset that contains 1 and 2. And we're looking to see what gets hit out of that subset. So what is the image of C under H.
Professor, why is A going into C and not B?
Let me see. Did I not, let me check. Did I do something wrong? One go, yeah. Hey, nice job. Extra credit. The reason it's not going where it's supposed to is the old Dr. Good is slipping. She's slipping. Email me for that. Thank you. Let's fix it. Nice. Somebody's actually awake. One is supposed to go to B. Ah, nice. That's going to make a difference, isn't it? Very good. Is that right? Do I have it right now?
Yeah.
Yeah, excellent. So what is the image of C? In other words, let's look at the arrows coming out of this subset C. Where do they go? What do they hit? What elements are getting hit? Anybody?
B, C.
5 and 2.
B and C? Did I hear B and C?
I said B, C, E.
B, C, and E.
Yeah.
Okay, that's the range of H. The range of H is B, C, and E, but we're asking for the image of just this subset of X.
That's B and C.
Just B and C, right? See, because one maps to B, two maps to C, and that's all we're looking at. We're just, we're just looking inside this little red subset and asking, where do the arrows coming out of this little red subset go? And they hit B and C. So since H of 1 is equal to B and H of 2 is equal to little c, H of the subset C is the set containing little b and little c. Everybody with me? All right, so I'm gonna give you a couple more sets C, and you see if you can find H of C for these sets C, okay? What if C has got 3 and 4 in it? And what if C has got 2 and 5 in it? And here's the definition of the image. There, everybody can find those. Since H of 3 is E and H of 4 is E, H of this C, we could call, we could call this C1, C2, and C3 since they are different. Why don't we do that? This will be C1, C2, and then it'll be C3. H of C2 is, I'm just getting the singleton set E for H of the second C2, right? Is that what y'all are getting?
Yes.
Thank you. And finally, what is H of C3?
C,
So you can, yeah, it's just little c. You can look at the arrow diagram, but you can also just look and see where 2 mapped to, 2 went to C, right? 5 went to C, so you know that C is the only thing that's getting hit out of this subset of the domain, right? All right, so now shall we play the inverse image game? Let's play the inverse image game. So here's the definition of the inverse image. We're going to look backwards and see what elements hit the elements in D. Okay. So find H inverse of D, where, okay, for our first one, let's let D, I will call it D1, be the set containing A, B, and C. So what we're doing is we're looking backwards to see what hit A or B or C. Here's our, let me fold this out and get it out of your way. Here's our definition. It'll be the elements over in the domain. The domain here is called X, not A, doesn't matter. Such that F of those X land in D. So we're just asking what elements have arrows that land in this subset D1. I'll draw, so we're looking at this subset of the codomain. It's got A, B, and C in it. So we just look at the arrows that landed inside this green subset and find the X elements that shot those arrows into this green subset that contains A, B, and C. So what would that be?
Would it be the elements 1, 2, and 5?
Yeah, 1 maps into D1 because it hits little b. 2 maps into D1 because it hits C. And 5 maps into D1 because it hits C. Right? So H inverse of D is the set containing 1, 2, and 5, since H inverse of A was nothing hit it, but H inverse of B was the element 1, and H inverse of C was both the elements 2 and 5. So 1, 2, and 5 send their arrows in to hit this subset, these elements in this subset. Questions? Should we do another one? Let's do a couple more and just make sure everybody has got it. How about D2? Let's let D2 be the set containing A and D. These are subsets of the codomain Y. So what elements back here in the domain hit A or D? Anybody? Little a or little d? Did anything hit A? Does any arrow hit A? Nope. A does not appear as the second coordinate anywhere, so nothing is hitting A. What about little d? D does not appear as a second coordinate. It does not get hit by an arrow. So guess what? Oh, this is D1. H inverse of D2 is empty because the inverse image of A is empty because nothing hit A, and the inverse image under H of D is also empty. No arrows hit either one of those. So the inverse image of this subset is the empty set. And finally, for D3, wow, I'm going to have to steam that piece of paper or iron it or something to get it flattened out to scan. Let's do one more. D3 is going to be the set containing E. What is the inverse image of D3?
Three and four.
Yeah, because 3 and 4 both map to E. 3 hits E, and so does 4. So the inverse image of just the singleton set E is the set that has 3 and 4 in it. Questions? Okay, so that's it for images and inverse images. That is section 7.1. And now we are ready to start section 7.2. Properties of functions. There are two famous properties